Hi everybody. In this chapter we're looking at sequences and series. In this lesson we're going to be looking at infinite geometric series.
Alright, so here we go. We're going to start this with a discussion. And the intention here is to kind of give you a sense of kind of a little bit of the history of this idea and some of the issues here. Now we're going to start with a discussion about a guy named Zeno. Now what I'm going to show you here is kind of an adaptation of what this ancient philosopher was saying here. So let me give you an example here. Let's say that you've got, and I'm going to do this in kind of a modern day take on this. Let's say that you've got the Flash. Okay, here's the Flash. And the Flash is going to have a race with a turtle. Okay, there's my turtle. So the Flash is going to race the turtle. Now, though the Flash, being a really nice guy, looks at the turtle and says, look, you can have a head start. So he gives the turtle a head start. Then, when the Flash takes off, this is how Zeno saw what was going on here, okay? When the Flash takes off, regardless of how fast the Flash goes, it's going to take him a little bit of time to cover this distance that he has given the turtle as a head start. In that amount of time, the turtle will have moved forward a bit. Okay? Now, once the Flash hits here, the turtle's now up here. So it's going to take the Flash a little bit of time to cover that distance. But in that amount of time, the turtle still moves forward, turtle moves there. And so the Flash has got to take a little bit of time, regardless of how fast he goes, to get to that point right there. And in that time, the turtle has moved forward a little bit. And Zeno argued that this continues on and on and on forever. Now, his conclusion is, at this point here, that the Flash can never ever catch up to the turtle, because this can happen an infinite amount of times. Each one of those little pieces is going to take a little bit of time to cover. You add up all that infinite amount of time, that is an infinite amount of time, and there's no way then that the Flash can catch up with the turtle. Now, his colleagues would have looked at him and said, Zeno, look at me, watch, I'm not the Flash. And you run up and you give the turtle a kick. He says, I caught the turtle. In fact, I'm ahead of the turtle now. And Zeno's response would have been to look at them and says, I know, right? I can catch the turtle too. So where am I wrong? Okay, where am I wrong in my thinking here? Where I'm concluding that it's impossible to catch up. Where have I made the mistake? Because obviously it is. And that's where we call this a paradox. Okay? Now, let me illustrate a similar sort of idea here in just a slightly different way. Let's take a quick look at, cover this up here, let's take a quick look at a square. And let's just say that this square has sides 1 and 1. Now, when I cut this in half, okay, the area of that piece will be 1/2. If I cut it like this, the area of that piece is going to be 1/4. And I'm going to add up these pieces here. I take that, it's 1/8, and I cut it like this, and this is going to be a 1/16. I cut this, and it's going to be a 32nd. And I can just keep doing this forever and ever and ever. But now think about this. I'm never going to get pieces that are outside of this box. They're always going to be inside the box, and I'm going to be zeroing in this little corner here. If I was to allow this to go infinite, okay, and I could get an infinite number of these pieces, what would the sum be? And the answer is the sum would be 1. When you add up 1/2 and 1/4 and 1/8 and a 1/16 and a 32nd, the sum is 1. Now notice, each one of these little pieces here has got a little bit of size to it. Okay? And when you add them all up, you still get just a finite number. And right there, that is the essence of the mistake that Zeno's making here. Zeno assumes that if you add up an infinite amount of pieces, a number of pieces, even if they're getting smaller, his conclusion is that the sum is infinite. But that's not necessarily true. And so this leads us, okay, to a way of thinking here. Now let's zoom out a little bit. Okay? So it is possible for a series, an infinite series even, to have a finite sum. And so when a series has a single, and that's important, finite sum, we call the series convergent. Okay? If a series does not converge, and I love this definition here, okay, we call it divergent, and that's basically does not converge. Now I want to talk about this really quickly here. This idea of single might seem a little odd here, but watch this. If I've got this, just to illustrate this, if I've got the sequence 1 minus 1 plus 1 minus 1 plus 1 and so on, what is the answer? Well, at first blush you might think 0, because you've got 0 plus 0 plus 0 and so on, and an infinite number of zeros would give you 0. But I can, by just simply covering up this first number, I can offset that, and I get negative 1 plus 1 is 0, negative 1 plus 1 is 0. I get an infinite number of zeros plus that first 1, and the answer is 1. So the question is, what is it? Is it 0 or 1? And as a result, because I don't get a single finite sum, this is what we call divergent. Okay, so diverging can mean a couple of things. It can either mean going off to infinity, okay, or it could be that it just simply doesn't get a single sum. It's getting, like, there's two values here. And in fact, you'd see that in some contexts, people argue that there's actually even a third possibility here. But anyway, now, when we talk about a geometric series, we're just going to lead you through this here. A series converges if the common ratio is between negative 1 and 1. And I'll illustrate that in just a second. Okay. The issue here being that if you've got a common ratio between negative 1 and 1, when you multiply it by itself over and over again, you get a smaller and smaller value. So take a quick look at this. 1/2 to the 1 is a half. 1/2 squared is a quarter. Okay, well, that's smaller. 1/2 cubed is an eighth. Smaller, even smaller. 1/2 to the 4th is 1/16, and so on. The larger the exponent gets, the smaller this power gets. And in fact, and this is the essence of it. Now this is kind of hinting at an idea that you'll look at in a lot more detail in a calculus course. But when the value of the common ratio is between negative 1 and 1, as the power gets larger, the result gets smaller. And in fact, if we let n go off to infinity, and that, remember, n is the exponent here. If we let the exponent on that fraction go to infinity, it turns out 1/2 to the n, or basically any fraction that's between negative 1 and 1, is going to become 0. Okay? And so what that allows us to do here, and I'm going to zoom in on this. Whoops, wrong way. This is the sum of a geometric series up to n terms here. But if we let n go to infinity, well, first of all, what we do with our notation is we no longer put a subscript there. When you see an s like this all on its lonesome, that s means an infinite sum. What happens here is this term right here goes to 0. And so you get 0 minus 1 times a over r minus 1. So negative a over r minus 1. And then what we do is we move that negative down to the denominator to make this a over a positive. We start with a positive up front, 1 minus r. And that is the sum, okay, of an infinite geometric sequence, as long as r is between negative 1 and 1. And so that's our conclusion right here. Now, important point. If the r value is greater than or equal to 1, and actually we might even state, I should probably have done it like this, if the absolute value of r is greater than or equal to 1, this does not hold. Okay, in this case here, the sequence either increases without bound or it alternates with larger and larger values if it's negative there. So either way here, if that's true, then we say that the sequence diverges.
Identify whether the sequence 1 plus 1/3 plus 1/9 and so on is convergent or divergent, and if it is convergent, find its sum.
Okay, well, before we can tell whether this converges or diverges, we have to know what the r value is. So let's take a quick look at this. R is going to be the second term divided by the first term, or the third term divided by the second term. So 1/3 divided by 1 is 1/3. So therefore, I know that this converges because this is inside that interval that I'm interested in. And so now I can use my sum here. My a value was 1, and I'll subtract r. So 1 minus 1/3 is going to be 2/3. And when you divide that, 1 divided by 2/3, basically just forming a reciprocal here, this becomes 3/2. And so there's my infinite sum, 3/2.
Determine if the series 1 minus 5 plus 25 and so on is convergent or divergent, and if it is convergent, find its sum.
So in this case here, to determine whether or not this diverges or converges, I got to know what r is. So let's take that second term there, negative 5 divided by 1, and I'll get negative 5. Now, that is outside that interval that I'm looking for, so therefore I would say, without doing anything else to it, I'm just going to say that this diverges.
Identify whether the series 2 minus 1 plus a half and so on is convergent or divergent, and if it is convergent, find its sum.
So to determine whether or not this one is converging or diverging, once again, I got to look at my r value. Let's take a quick look here. Now, 2 minus 1, so I'm going to take the second term there, which would be negative 1. I'll divide by the first one, and actually there it is right there. It pops right out. My r value is negative 1/2. Because that is in between negative 1 and 1, I know that this converges. Now, the negative here is important. So my infinite sum, s, is going to be 2, okay, the first term, over 1 minus negative 1/2. And I need that negative in there, okay? I need to maintain that negative with the r value. So this becomes 2 over, well, 1 minus negative 1/2 is really just 1 plus a half, or 3/2. And so it's like multiplying by the reciprocal, and the answer is you get 4/3. And so there's the infinite sum there, 4/3.
The sum of an infinite sequence is 12.5. If the common ratio is 1/5, find a.
So you can expect to bump into a problem similar to this at some point in time here. Really what we're doing here is just using this formula, and we're going to start to give you different pieces of it just so that you can practice the algebra. So in this case, we know that the infinite sum is 12.5. We know that the r value is 1/5. Okay, what we don't know is a, so we just want you to go through and solve for a here. Well, let's simplify the denominator first. Okay, so we're going to get 12.5 here is going to equal a over, well, 1 minus 1/5 will end up being 4/5. And then we're just going to multiply that across, okay? So we're going to multiply 12.5 by 4/5, and it turns out you get 10. So it looks like the first term in this particular infinite sequence is 10.
The first term of an infinite geometric series is 2, and its sum is 4. What is r?
Very similar to the previous question, what we're doing here is we're taking a look at this particular equation or formula here. You're going to be given a couple pieces and asked for what's missing. Now in this case here, we know that the first term is 2, and we know that the sum is 4. So 4 is equal to 2 over 1 minus r. We're going to solve for r here. Now, what I'm going to do here, this is a rational expression right here, so I'm going to multiply numerator and denominator by 1 minus r to get rid of the denominator. So that's 4 times 1 minus r is equal to 2. I just about wrote that wrong, but anyway. Distribute that through. 4 minus 4r is equal to 2. Bring that 4 over, so negative 4r is going to equal negative 2. And when you divide, we get that r is equal to 1/2. So just a little bit of manipulation of that formula here, we can find the piece that we're looking for. This is a much simpler equation than the sum of a finite sequence.
Write 0.07 repeating as a fraction.
So here's an application of the use of infinite geometric series here. That's kind of a neat one. So 0.07 and the bar on top there means repeating. So this is going to be the same as, oops, sorry, I wrote that out wrong. This is going to be the same as 0.07777 and so on. Now let's take a quick look at that and let's tear this thing apart a little bit. So what this means is this is going to be the same as 0.07 plus 0.007 plus 0.0007 and so on. And this can be written as 7/100ths plus 7,000ths plus 7/10,000ths and so on. So an infinitely repeating decimal can actually be written as a series, okay, a geometric series, an infinite geometric series. Our first term here is going to be 7 over 100, and because if you take a look at these terms here, the difference between, or sorry, not the difference, the ratio between them is just going to be 1/10. Every time I go from one term to the next, I'm going to multiply by 1/10 here. So r is 1/10. So now this sum, which by the way we already know is going to be 0.0777777, is going to be equal to 7 over 100 divided by 1 minus 1/10. So that's 7 over 100 over 9/10. And when you multiply by the reciprocal here, okay, we're going to bring that 10 up. 10 will cancel here. We're going to get 7 over 90. And that's the fraction that we're looking for.
Write 0.231 repeating as a fraction.
In this case, we're going to look at the same question as we did previously, but in this case, it's a little bit more complicated what's being repeated. Whoops, sorry, 231, 231, 231, and so on. And so this can be written out as 231 over 1,000 plus 23, well, actually, sorry, that's okay, plus 231 over, well, if I go over 1, 2, 3, 4, 5, 6 over 1,000,000 plus 231 over 1,000,000,000 and so on, right? Because what's happening here is this is a group of 3 digits, meaning, okay, our first term here, granted, is 231 over 1,000, but our R value is also going to be 1 over 1,000, okay, because we're changing by 3 digits there. Whoops, sorry, you can't see that. So now we know that our infinite sum is going to be equal to this 0.231. The first term is 231 over 1,000, and our R value is 1,000th. So in the denominator, we can simplify that a little bit by making that 999 over 1,000. Okay, and now when you reduce that, okay, the thousands will cancel. We're left with 231 over 999. Now, that's great, okay? However, 231 over 999 can be reduced. They're each divisible by a factor of 3 here. So we're going to get, what is that, 77 over 333. Actually, I'm just going to double check. I don't think that can be reduced any more than that. Right off the top of my head, I don't believe it can be. Nope. So that's it. So 77 over 333, that is the fraction form for that particular repeating decimal.
Consider the ball problem from the last 2 lessons. Dropped from a height of 70 meters, bouncing to 80% the previous height. Through what distance does the ball move if it is left to bounce indefinitely?
Okay, so here's our last time to look at this little ball here. So once again, remember how this works here. We're starting with a height of 70. It's going to keep going here. We're starting at a height of 70 meters. And we have stated, whoops, sorry, on a couple of occasions here that we've looked at this, that we're going to make that our A. It doesn't have to be our A, but we're going to make it our A here. And then we know that our R is going to be 80%, so 0.8. Okay? That's what we're multiplying by. Now notice that this is inside that range that we're looking for an infinite geometric sequence here. So this is going to converge. Okay, so therefore this is going to converge. So our infinite sum here would be 70 over 1 minus 0.8. Okay, I'm just going to run to my calculator here and do this real quick. So 70 divided by 1 minus 0.8, and we get 350. Now, but remember what this is. This is just the sum of height, 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 height. So if we want the total distance traveled, we're going to take our infinite sum here, but we're going to multiply that by 2, because every time the ball bounces, it goes up this height and then down. It goes up this height and then down. So it's doubling up every one of those, except for the original. So what we're going to do here is we're going to subtract the 70 from this. So this is going to be 2 times 350 minus 70. Okay, well 2 times 350 is going to be 700. Minus 70 will be 630 meters. So the total distance that this ball will travel if we let it bounce indefinitely will be 630 meters.